All right, guys, it's 10 o'clock. We're going to get started today. Thank you guys for being here. If you would, please someone unmute your microphone and let me know that you can hear me and that you can see my screen.
We can hear you.
Awesome. So please, during the session, mute your microphone, turn off your webcam. That just makes Google Meet work better. Anytime you have a question, feel free to unmute and ask it. We are recording this session, and that recording will be posted to the A+ College Ready Science YouTube channel. If you haven't checked out that channel, there's all kinds of videos there that probably will help you a lot with AP Physics 1. We'll have the same thing going on next week, week 5. It'll be on Friday, next Friday, the September 25th at 10 o'clock. Today, though, we're talking about projectiles mostly, and we're going to be looking at projectiles in 2 dimensions. So we're going to start off with the problem. Here's where we're going to start. So we've got a projectile that's launched at an angle above the ground. It's a cannonball in this case. It's launched at a 45-degree angle above the horizontal and to the right. It starts off with an initial speed of 50 meters per second. And what we're asked first, what is the horizontal component of the cannonball's velocity? How does this change over time? Why is this true? So whenever we have a problem like this of a projectile shot at an angle, we first of all need to draw a horizontal. Then we need to draw in a vector that represents our cannonball. So our cannonball is being shot at a 45-degree angle above the horizontal and to the right. So that might look something like this. This is a 45-degree angle with the horizontal, and it's being shot with an initial speed of 50 meters per second. So maybe something like so. The next step you always want to do is you want to take that initial speed, that initial velocity, and you want to break it into a horizontal and a vertical component. We're doing called vector resolution. And the way we do that is we go to the end of our vector and simply draw down a vertical. We're going to call this leg of the triangle we've now created the vertical component, the y component, and this leg is going to be the x component. We're going to solve for those components using trig. Since we're at a 45-degree angle, the components are going to be the same. That typically won't be true. It's only true at a 45. We're asked first to find the horizontal component, which would be x. So to find that, we're going to use the trig function cosine. And we're going to say that cosine of 45 equals our adjacent side of our triangle, x, over our hypotenuse, which in this case is 50. So we're going to say the cosine of 45 times 50, solve for x, and we're going to end up with x equal to 35.4. And that's meters per second. And that would be toward the right. Remember that velocity is a vector, so you need a direction. You could just put plus 35.4 because plus means to the right in this case. So that's our first part of our answer to part A. We've got the horizontal component. Next part of the question, how does that change? Well, it turns out velocities only change, acceleration only happens when there's a force, a net force acting in that direction. In these physics problems, we typically always ignore friction and drag unless you're told otherwise. So if that's true, if we're ignoring friction and drag, there is no horizontal force. Since there's no horizontal force, there's no horizontal acceleration, which means the horizontal component starts off at 35.4 to the right, and throughout the entire problem, it remains 35.4. So the answer to how does it change over time, it doesn't. And the reason that that's true is that there's no horizontal net force acting on that cannonball. Now let's do the same thing with the vertical component. So to find the vertical component, instead of using cosine, we would use sine. And we'd say the sine of 45 equals our opposite side, which is y in this case, over our hypotenuse, 50. Solve that out, and we end up with y equals positive 35.4 meters per second. and that would be in the upward direction. So that cannonball is going 35.4 meters per second up and 35.4 meters per second to the right. So the ball's initial vertical velocity, 35.4 meters per second up. How does this change over time? Well, this one's going to change because there's a net force acting on that cannonball in the vertical direction. And that net force is gravity. So that as soon as that ball leaves the cannon, it's going to be its vertical component is going to begin to accelerate at the acceleration due to gravity, which is negative 10 meters per second square. So how does it change over time? That component is going to change. It's going to accelerate at negative 10 meters per second square. And the why is because there's a net vertical force acting on that cannonball. And that net vertical force is gravity. Before I go any further, because there's some more parts to this problem, are there questions on these first two parts by anybody? All right, let's go to the next part then. So next we want to know, how long does it take the ball to return to its original launch height? So essentially, how long is the ball in the air, the cannonball in the air? What you've got to remember here is that when you're thinking about time in the air, that's determined by the vertical components of the problem. Remember, we started off with an initial vertical speed of 35.4 meters per second. Vertically, that ball is going to go up and it's going to come back down. It left the ground with a speed of 35.4 meters per second. And when it gets back to the ground, it turns out its speed is going to be negative 35.4 meters per second. And the reason that's true is on the way up, it's accelerating at negative 10. On the way down, it has the same acceleration, negative 10. So it's going to have the same velocity when it returns to the ground as it did when it left. I should say the same speed. The direction is in the opposite direction. So we had plus 35 on the way up, negative 35 on the way down. So point being, our final velocity is negative 35.4. We know that our acceleration is negative 10 meters per second square. We're looking for a time in the air. And the easiest kinematic equation to use to find that time would be this one. Final velocity equals initial velocity plus AT. I like to solve my equations out for the variable I'm looking for before I put in any numbers. So I'm going to solve that for T. So I would subtract the VO from both sides, and I would divide both sides by A and rearrange my equation to get this. Once I've got that rearrangement made, now it's just plugging in. Final velocity, negative 35.4 meters per second, minus the initial velocity, which was positive 35.4 meters per second, all divided by our acceleration, which was negative 10 meters per second square. When I plug that into my calculator, I end up with a time, and this is a total time in the air of 7.08 seconds. So that would be my answer here, 7.08 seconds. Next thing I'm asked is what range does the ball cover? The range is the horizontal displacement. And remember that during a projectile problem like this, if you ignore drag, the horizontal speed is constant. So when you have a constant velocity problem and you're looking for a displacement, this is the equation you typically want to use. Delta x equals VT. So our range is going to be delta x, and that's equal to our horizontal velocity, which is positive 35.4 meters per second, times our total time in the air of 7.08 seconds. We do the math on that, and we end up with a horizontal displacement, or in this case, a range of about 251 meters. All right, next we're looking for what maximum vertical height does the ball reach. There's several kinematic equations we could use to work this out. I'm going to make some space to do it. maybe the easiest way to do it is to use this one. And like I said, there's other ones you could use as well. This is final velocity squared equals initial velocity squared plus 2a delta y in this case, because we're going vertical. And what we want to think about is we're trying to find the maximum vertical height. So the ball starts here and it ends up here. Here the speed is 35.4. But at this height, this maximum height, the ball is stopped. So that's what we're going to use as our final velocity is 0. So we're going to say 0 squared equals 35.4 squared plus 2 times a times delta y. And we're looking for delta y. So we've got to solve this for delta y. So I'm going to go 35.4. I'm going to square that. And actually, I should subtract that from both sides. So I'm going to end up with negative 1253.16. So this is my 35.4 squared, and I just moved it to the other side by subtracting it. And that's equal to negative 20, 2 times negative 10 times delta y. So I needed to divide both sides by negative 20. And I end up with a delta y here of about 62.7 meters, positive 62.7 meters. That's the maximum vertical height. All right, and then finally, what's the ball's resultant velocity as it reaches the launch height? So what we're being asked here is that the ball goes up and then it comes back down. And what's its actual velocity when it gets back to the ground? So we know that the whole time it has a horizontal velocity of positive 35.4. All right. And when it gets back to the ground, its vertical component is negative 35.4. That's when it returns back to the ground. It's the vertical component, which is what we're asking for here. So we're going to draw this tip to tail like so. We're going to draw in our resultant starting at the tail of our first vector to the tip of our second, like that. This is our resultant, which represents our sum. And we're going to solve for that using the Pythagorean theorem. So we'd say r squared equals 35.4 plus 35.4. And that actually be negative 35.4, but it doesn't matter here because the negative is going to square out. Solve that out for r, and we end up with, let's see, what do we end up with? Turns out 50 meters per second. And that makes sense because the speed ends up being the same speed that we started with. But we're asked for the velocity. This is just the speed. Velocity is a vector. It needs a magnitude and a direction. And remember, the direction that you want to use is the angle between your resultant and the horizontal. That angle right there, we'll call it theta. And we'll solve for that angle by using a tangent would probably be the easiest way. So we're going to say tan theta equals opposite 35.4 over adjacent 35.4. We'll take the inverse tangent of 1 to get 45 degrees. So our answer here is going to be 50 meters per second at 45 degrees, and that would be below the horizontal and to the right. So that's how you would want to write out this answer. Our velocity is 50 meters per second, and we would want to write 50.0 with sig figs at 45.0 degrees below the horizontal and to the right. So that's a lot of work to get through that one problem. Are there questions I can answer for anybody about problem one? That's all the pieces that we're going to do on this problem. All right, well, let's go to the next one then. Well, before we do, so if the launch speeds are the same, A projectile launched at a 45-degree angle will travel further than projectiles launched at any other angle. Projectiles launched at an angle of theta and an angle of 90 minus theta will travel the same range. So let's say that we launched a projectile at 30 degrees. Well, it turns out that a projectile launched at 30 will go the same range as one launched at 90 minus 30 or 60. So these two angles will give us the same range. If we launch one at 20 degrees, it turns out that would go the same range as one launched at 70 degrees because 90 minus 20 is 70. So those complementary pairs will give you the same range or horizontal displacement. All right, so here's another problem. A baseball player throws a ball at 30 meters per second at an angle of 60 degrees above the horizontal and to the right. How long in seconds does it take the ball to return to its original launch height? Assume the ball returns to the height from which it was originally thrown. So again, first thing, draw in a horizontal. Well, that's a terrible horizontal, but we'll go with it. Next, draw in a vector that represents what's given to you in the problem. So a 60-degree angle and 30 meters per second is our speed. We're looking for time in the air. Before we do anything else, we want to draw in the vertical and horizontal components of this initial velocity. So we draw down a vertical like so. We're going to solve for the y component, the vertical, and the x component, the horizontal. To solve for the vertical, we're going to say sine 60 equals opposite, which is y, over hypotenuse, which is 30. We do the math on that. And when we do, that gives us a vertical speed, an initial vertical speed of 25.98 meters per second. And that's in the upward direction, 25.98 in the upward direction. We're also going to go ahead and solve for the cosine, solve for the horizontal component. So cosine of 60 is equal to the adjacent side, x, over 30. So the cosine of 60 is 0.5 times 30. We end up with an x velocity of 15 meters per second, and that is to the right. Now, it turns out that the time in the air is always determined by the vertical component. So remember it this way. We're going to start off going up at 25.98. As soon as it starts up, it's going to accelerate at -10. So eventually up here, it gets to a speed of 0 at its maximum height. Then it starts back down, starting at 0, accelerating at -10, and eventually it ends up here with a final speed back at the ground of -25.98. So just like we did in the first problem, the easiest equation to use to find the time is final velocity equals initial velocity plus AT. Solve that for T. So that's our equation solved for T. And then plug in our numbers. Our final speed is going to be the speed that it hits the ground at, which is -25.98. Minus our initial speed, which was positive 25.98, divided by our acceleration, which is -10. Solve that out, and we're going to end up with a time of 5.20 seconds. So that's the total time in the air, 5.20. We're going to go to the next part of the problem here, remembering that our horizontal component of our speed was 15 meters per second, and our time was 5.20. So I'm going to write Vx, 15 meters per second. That's my horizontal component of my velocity, and my time in the air was 5.20, and my vertical component, my initial vertical component was, let's see, what was it? 25.98 meters per second. So let's see what we need in problem 3. Same problem. This time we just want the range. And this should say assume the ball returns to the same height. So the range, remember, is the horizontal displacement. The ball is moving horizontally with a constant velocity of 15. When we're dealing with constant velocity problems, this is the equation we want to use. Delta x equals vt. So we're going to say that our range, our delta x, is going to be equal to our horizontal component of our velocity times our total time in the air, 5.20 seconds. And all we need to do is multiply that out. And when we do, it looks like that comes out to be about 78.0 meters. And we should say positive 78. It's to the right. 78 meters to the right. All right. Any questions from anyone about problem 2 or problem 3? Make sure you ask if you have questions. I'll be glad to answer them. All right. So problem 4 is another part of the same problem. This time we want to know what maximum height does this should say the ball get to. And that's all determined by the vertical stuff. So remember that our initial vertical velocity, we'll call that VOY, was 25.98. We're accelerating, the acceleration due to gravity, negative 10. And we're trying to find a maximum height, trying to find a y. So there's several ways we could do this. Maybe the easiest way would be to think about the time. So remember, our total time in the air was 5.20 seconds. That's the time up and the time down combined. Since the acceleration is the same on the way up as it is on the way down, the time on the way up is the same as the time on the way down, which means it takes 2.6 seconds to get up and 2.6 seconds to get back down. We're really only concerned about the upward part of this. We know that we're starting off at this speed, we're ending up at a speed of 0, and that between there and there, we're accelerating at negative 10. And we're trying to find a displacement. So maybe the easiest way to find that would be delta y equals VOT plus 1/2 AT squared, where our initial velocity is 25.98 meters per second times our time of 2.6 seconds plus 1/2 times negative 10 times 2.6 seconds squared. All right, if we do the math on all that, it's looking like we end up with a maximum height of about 33.7 meters. So the ball goes up 33.7 meters, and we calculated in the previous problem that it went out to the right 78 meters. All right, so let's go on and look at problem 5. And this makes you think about these vertical and horizontal components. The figure to the right depicts the trajectory of a kicked football. Which of the following correctly ranks the speeds of the ball at the 4 locations? Now notice, speed. So direction here doesn't matter. This is the net speed. We got to remember that at point A, this thing is just coming off the kicker's foot. It's got a pretty fast vertical velocity and a constant horizontal velocity. And we know as it goes up, it's accelerating at negative 10. So on the way up, its vertical velocity is decreasing and its horizontal velocity isn't changing, which means B is going slower than A. Here it's at its maximum height, which means its vertical velocity is 0. Its horizontal velocity is constant, which means that B is greater than C. And what we got to think about now is D. So on the way up, acceleration, negative 10. On the way down, acceleration, negative 10. if we can assume that B and D are at the same heights, their speeds should be the same, which means this. A is greater than B, which is equal to D, both of which are greater than C. So our answer on this one would have been B. Anyone have questions on why that's true? All right, so another question from the same diagram. Which of the following best indicates the direction of the acceleration of the ball at position B? What you guys have to remember is that acceleration is caused by net forces. And the only force acting on this ball, assuming we're ignoring drag, is gravity. Gravity always acts straight down. So it doesn't matter if this question asks about the direction of the acceleration at A, B, C, or D. In every case, the direction of the acceleration is the direction of the net force. Since that's gravity, that's always straight down. Answer B would be what we're looking for on this one. All right, so we're going to wind up today by talking about this FRQ. So a group of students measured the vertical and horizontal components of the velocity of a baseball as it traveled through a parabolic trajectory. So we know the ball is going to go something like this, parabola. The data is presented in the table to the right. Graph the vertical velocity versus time. So it's asking us to graph this against this. So this would be our Y, and this would be our X. I went ahead, since it's hard for me to hand draw a graph on the screen, I went ahead and did that. So here's my graph. This is part A. So notice that we've got a negative slope. Let's go next. Find the slope and the y-intercept of the graph in part A. We can do that without looking at the graph. We know to find slope, we're going to go change in y over change in x. So I'm just going to take the first and last points. So I'm going to say negative 7.5 minus 3.58. That's my last and first y components over my last x component, 0.5, minus my first x component, 0.1. So if I do the calculation on that, so negative 7.5, that's going to end up being plus, because we have minus a minus, plus 3.58. And I'm going to end up dividing that by 0.4. And it turns out my slope comes out to be negative 9.8. And since this is in meters per second, and this is in seconds, and I'm dividing those, that would be meters per second square. Well, I'm hoping that looks familiar to you, because that's the acceleration due to gravity. We use negative 10 usually in physics 1, but more precisely, it's negative 9.8. So now we have the slope. That makes sense because the slope of a velocity versus time graph represents acceleration. This is the acceleration that's happening. Now we're also asked to find the y-intercept of this graph. So the easiest way to find that y-intercept would be to use the slope-intercept equation, plug in our slope, which is negative 9.8, put in any one of our y components. We'll just start with the first one. So negative 3.58 times our x component, for that one is 0.1, plus b. Remember, b is our y-intercept. So let's solve this out for b. So that's going to end up being, when we do the math on this, it's going to end up being negative 3.58. And we're going to end up having to add 0.98 to both sides, because 9.8 times 0.1 is 0.98. So we're going to end up with a y-intercept of about negative 2.6. And I've notated that on the next slide. So slope, negative 9.8, y-intercept, negative 2.6. Next part of the question asks me to write an equation that describes the graph of part A. Well, again, we know that the equation for a line, at least the slope-intercept form, is y equals mx plus b, where m is the slope and b is the y-intercept. So we're going to say y equals our slope, negative 9.8, times x, plus our y-intercept, which was negative 2.6. So that is an equation for this line, our vertical velocity plotted against time, the vertical component of our velocity plotted against time. All right, next, we're asked to, on a separate graph, plot the horizontal velocity, which you see is constant, against time. I've also done that on a sheet of paper to make life a little easier on us. So here's my horizontal velocity against time. Notice we got a nice straight horizontal line, which means the slope is 0. We're next asked to write an equation that describes the graph from part D. Well, let's make a little space here. We could solve for y-intercept first of all. Y equals mx plus b. So let's just use our first y component and our first x. So our y is 4.22. Our slope is 0. Our x is 0.1 plus b. Since this is 0, that means our y-intercept is 4.22, which means when we write out y equals mx plus b, we end up with y equals 0x plus 4.22, which means y equals 4.22. That is the equation for this line, y equals 4.22. Y equals a number gives you a horizontal line. It's the equation for a horizontal line. All right, and then finally, is the baseball on its way up or down between t equals 0.1 and t equals 0.5? And justify your answer. So to know if it's on its way up or way down, we need to look at the vertical velocities. And notice that the vertical velocities are negative during that whole time interval. A negative vertical velocity means down. Also notice those vertical velocities are getting bigger. The speed is getting bigger as we go down time. That means they're accelerating. So we have a negative velocity and a negative acceleration. The speed is increasing. The answer here, it's on its way down, and we know that because the vertical velocity has a negative sign. That's our justification. The vertical velocity has a negative sign. And then finally, calculate the resultant velocity of the baseball at each time interval. So the resultant means we need to add together the vertical and the horizontal components. We're not going to do this for all of these time intervals because it works the same way. But let's do it for the first two. The easiest way to do this is to draw your horizontal in first. So we'll start here. Our horizontal component is 4.22. At that time, our vertical is negative 3.98. So we're going to do a tip-to-tail vector addition. We're going to go to the head of our first vector, put the tail of our second one. We're going to connect, drawing the resultant by connecting the tail of the first vector to the tip of the second. That represents our sum, our resultant. And we're going to say r squared equals 4.22 square plus 3.58 square. And we're going to solve that out. So 4.22 squared plus 3.58 squared. Take the square root of that whole thing. And we end up with r equals 5.53, and that would be meters per second. Now, a lot of you are going to stop and say, hey, I'm done. This is the resultant speed at that point. It's not a velocity because it doesn't have a direction. This is the magnitude. We also need a direction. And remember, the direction we want is the angle between our horizontal and our resultant. So that angle, call it theta. Solve for that angle by using tangent. So tangent of theta equals opposite 3.58 over adjacent 4.22. So let's go 3.58 divided by 4.22. Take the inverse tangent to get 40.3 degrees. And we would say that would be below the horizontal and to the right. So our answer would be 5.53 meters per second at 40.3 degrees below the horizontal and to the right. Let's do one more of these. Let's just go down to the bottom one and do the same thing. All right, so now we'll do this one. So we got this time and these velocities. So our horizontal speed is still 4.22. Draw that in first. Now connect your vertical velocity to that by going to the tip of the first vector and drawing in the second vector. Drawing our resultant by connecting tail of first vector to tip of second. That's r. Solve for r squared equals 4.22 squared plus 7.50 squared. Take the square root to get r equals 8.61. Again, that's the speed. That's not the velocity. We need a direction. The direction we need is the angle between our resultant and our horizontal. Once again, we'll find that using tangent. So tangent of theta equals opposite of 7.5 over adjacent of 4.22. 7.5 divided by 4.22. Take the inverse tangent or shift tangent on your calculator to get 60.6 degrees. That would be below the horizontal and to the right. All right. So any questions on this FRQ or any questions on projectile problems in 2 dimensions that I can answer for anyone? All right. Well, I thank you guys for being here. Again, we'll do this again next Friday, 10 o'clock, and we'll start dealing with forces and dynamics next week. Thanks again for being here.